see, testing. Can you hear me? Cool. All right. Good afternoon, everyone. My name is Megan Berry. I'm here from UC Davis. I'm a fifth-year grad student, about to be sixth year, also about to apply for postdocs. And I'm here to tell you today about how galaxies can form alpha element bimodalities. So first, probably most of you are wondering what is an alpha element bimodality. So I will go quite extensively through that before I get to any results. So first, when I say alpha element, that is as in a helium nucleus, as in alpha particle, and why those are relevant to us in astro, at least for my purposes, is that these are that elements formed from helium fusion are the primary products of core collapse supernovae. So this is not just the direct products of helium, but any subsequent reactions, the core collapse onion, etc. These are the characteristic products of core collapse supernovae that we can use to kind of trace these events. So when a core collapse supernovae goes off, it puts these elements out. It also puts out some iron that we'll treat separately for reasons I will explain. I feel like I have some feedback going on the microphone. I don't know. All right, so to get to the bimodality part, I'll have to introduce quite a bit of galactic element abundance evolution, which I think not everyone is familiar with, but I will try to keep it a bit simple. So there's three key principles that you should know in order to understand the basics of my results. So the first is that core collapse supernovae produce alpha elements and some iron on short timescales. So by timescales, I mean after star formation begins in some population, core collapse supernovae turn on quickly, and they also turn off quickly after star formation has begun. The second is that white dwarf supernovae produce iron on longer timescales. So not only so after star formation begins in some population, not only do white dwarf supernovae occur on a delayed start, they don't start until you have white dwarfs, but they also continue basically indefinitely after in that stellar population, because white dwarfs can hang around for quite a while. So you can hopefully already start to see how we can use these two supernova types with their different timescales and different characteristic element products to kind of trace the history of the Milky Way or other galaxies, where core collapse supernovae are kind of like a short-term timekeeping device like a clock, and white dwarf supernovae are kind of a longer timekeeping device like a calendar. And the third principle I want to make sure you guys know is how we can actually use these supernova products observationally to connect these to the evolution of a galaxy, and that is that stellar atmospheres preserve the element abundances of the gas they formed from. So whatever element abundances are in the gas in the galaxy at the time, when a star forms from that gas, those element abundances are preserved basically for the rest of that star's lifetime. So we can observe these, and combined with, for example, stellar age data, we can try to see how the element abundance of the galaxy evolved over time. Okay, so with that out of the way, I'll introduce now a plot that is widely used in the field of galactic element abundance evolution. So you can imagine plotting, every star in the Milky Way or whatever galaxy having a combination of two characteristic element abundances. Every star has some ratio of iron to hydrogen and some ratio of alpha to iron. With alpha, observationally, sometimes this is like an average of the alpha elements. Sometimes they just pick one. I picked magnesium to look at in simulations. Spoiler, this is a fire talk. So why do we choose these axes? So the x-axis, iron over hydrogen, we can sort of think of as a time axis, or at least like a proxy for a time axis, as we expect the amount of iron to generally go up in stars over time. And I'm sure you're already all thinking of ways that this may not be the case, but even then, you know that if the iron abundance starts going down in stars, then something happens to make it do that, some dilution or something like that. Then our y-axis, And again, sort of, because these are element abundances, and there's iron on both of these. That makes it a little difficult. They're little entangled variables, but sort of. The y-axis we can use to compare the relative history of supernova rates in the galaxy up into the point that star formed. So if a star is higher in alpha, that means there were relatively more core collapse supernovae in its history, in the history of that gas in that region of the galaxy. And if it's farther down on this plot, that means there were more white dwarf supernovae in the history of this galaxy. All right, so to see if you guys caught all of that, if you're still with me on this Friday afternoon, I have a quiz question for you that you can just answer to yourself. Don't shout it out. But I want you to look at this plot and guess where the oldest stars in the galaxy would be on this plot. Not population 3 for the smart Alex in the audience, just, the oldest kind of population 2. What have we? So I already gave you a hint. I already said older stars are going to be poorer in iron. So do you think the oldest stars would be higher up on this plot or lower down? Yeah, if you said higher up, you're right, because core collapse supernovae turn on first, and those are rich in alpha elements. So for early stars, we expect kind of an interesting floor that gives us kind of the ratio of alpha to iron in core collapse supernovae, which is kind of a whole separate cool thing. But then anyway, as time goes on, as we get more and more iron buildup, as white dwarf supernovae turn on, we get more and more iron in the denominator, and we expect younger and younger stars to go down over time. All right, so this is a basic picture of what we may expect, just using some very basic stellar evolution principles to predict how the element abundance of the galaxy might evolve. But if we take a look at actual data of this plot in the Milky Way, so same axes, we're going to populate this with stars from the Milky Way. What we see is that there's one population that looks kind of like what we said, but then there's also this separate, there's this whole second population in this space that is not, has no obvious reason to be there. So these two populations have come to be known as the high alpha population and low alpha population. And I won't get into this as much as I'd like, but you may also know that these are associated with the thick and thin disks of the Milky Way. But yeah, so this is the question that I'm trying to answer using the fire simulations, is why is there this bimodal population in this space? What makes the Milky Way different from our expected path through this element abundant space? And one more kind of new thing I'll point out is that, you may have already figured out that we don't have this measurement for that many galaxies because you need individual stellar spectra, but early results from Andromeda seem to indicate that it does not have this low alpha population, or it's not bimodal in this way. Maybe there's just not enough stars, maybe we didn't see enough, but it is very interesting that there seems to be a diversity of shapes in this element abundant space. Yeah, so we'd like to know what causes this, and is it ubiquitous among galaxies? Is it rare? Is it special? Just what is going on with this feature? All right, so to study this, I've been looking at Milky Way mass galaxies in the fire simulations. I won't spend too long here. I think we've already heard quite a bit about these, but these are cosmological zoom-in simulations with dark matter, gas, and stars. And importantly for what I'm doing, they feature self-consistent gas accretion, star formation, and metal enrichment. So I can use these to study detailed galaxy-wide element abundance evolution. All right, so let's take a look at, within the fire simulations, what does a fire simulation look like in this space? So this one does kind of look like what we expected based on our simple assumptions. So some of them do follow that more basic pathway. But I have been looking at these four galaxies that have what we've been calling a strong bimodality. It turns out there seems to be different degrees of this feature, and some of them kind of have like a sorta, that's a whole nother paper. I've been looking at these four galaxies to figure out the origin of basically this gap or this low alpha population, however you want to phrase it. So right off the bat, something that is just interesting is that some of the fire simulation galaxies have this feature. It's not all of them, not none of them, but just some galaxies have this, some of them don't. And again, future work is kind of looking at there's almost even a spectrum of this feature, I might say. We won't dwell too long on that. So let's, to kind of show what some of the analysis I've been doing is, let's look at this, that same plot, but binned into stellar ages, so we can kind of see how stars evolved through this space. So this will be, so we can see the oldest stars populating the top. These are all redshift 0 stars just binned into age. You can see and for the high alpha population, they do, take this diagonal path as we expect, but at some point, I'll play this one more time. At some point, the stars kind of spread out along iron, so those stars begin to get a wide diversity in iron, and then they all kind of go straight down in alpha. You can see it goes down normal, and then it switches to this kind of straight downward mode. So this is that same path, just smoothed and superimposed on the old plot. And we do see a similar path in all 4 of these galaxies, where the high alpha track kind of evolves as expected, and then it takes this, it veers down and to the right, and spreads way out in iron. And that's not, it's not obvious that it would have been like that, like some other models would predict, going down here and then going back here through some dilution event or something, and then, going back down the second path. So it's not that. We see something like this in all 4 of these galaxies. So we can say all of these galaxies go straight down in iron, straight down in alpha at fixed iron. And a little more insight into that is if we bin these into stars by their distance from the center of the galaxy, you can see this dark green is closest to the galaxy, this light green is the outskirts. You can see that this probably has something to do with the onset of the disk and the radial gradient, and as well as some kind of ongoing accretion we see balancing the, causing stars on the outskirts to get reduced in iron relative to those in the middle. So something to do with disk formation. And then real quick, the last thing, I have so many more results. I have thin and thick disks and all kinds of fun stuff you can see in the paper. The last thing I'll point out here is that one thing we saw in common between all 4 of these galaxies is that this transition from high to low alpha occurred right after a drop in the star formation rate. So I'm going to show the star formation rate here. This is look back time, so this is going back in time to the right. I highlighted, this is the time over which it transitions from high to low. So this is when it's going down. And if we look at the star formation rate, we can see this galaxy had this bump here. And in this case, this was from a tidal tail from a satellite. So another interesting thing I don't have that much time to touch on is that sometimes it's thought that this was basically a result of a merger, or that this feature was maybe like a indication of the GSE merger or something like that. And we find that you don't actually, one of them has a merger, most of them are kind of more sort of merger or not even at all related merger cases. Anyway, and we can see that this stands to reason that this would cause these galaxies to drop in alpha, because when the star formation rate goes down, this blue curve is the relative rates of white dwarf to core collapse supernovae. So we get the white dwarf rate kicks up relative to core collapse, or really more like the core collapse goes down, and this explains why these galaxies are going straight down. I have some stuff on the gas fraction I don't really have time for. These seem to be kind of gas-poor galaxies. Might have something to do with it. But I am low on time, so I will summarize that we find that some Milky Way mass fire galaxies have this feature. Not most, not none, but some galaxies have this, some of them don't. They all have this characteristic kind of straight drop in alpha at fixed iron, where they kind of spread out along a radial gradient. They all transition after a decrease in the star formation rate. Most of them have a relatively low gas fraction, and I have much more in my paper I'm hoping to submit before the end of the summer with looking at the thin and thin disks and what the individual merger histories of these galaxies were. There's only one has kind of like a big major merger, the other 3 don't really. And thank you.
we'll take one question while the next speaker sits up.
Very nice work. Quick observational question. Do other nearby galaxies, Milky Way mass galaxies, show this bimodality? And do those also have an indication that there was a drop in star formation rate? In other words, is there any observational correlation of your work with
That is a
nearby
very
galaxies?
good question. To my knowledge, there's an upcoming survey called Geckos that looks really cool, and they're using edge on, the Geckos is something like galaxy edge on something, where they use edge on galaxies to kind of look at abundances in the thick and thin disks to kind of suss out this feature, I think, among other things, but that's still upcoming. Otherwise, to my knowledge, the only disky galaxy we have this measurements for is Andromeda so far. And then, some Milky Way satellites, but that's a whole different. It is. It doesn't seem to be. It's very early. Yeah. It looks like not. Probably not. But maybe somebody will find some stuff in the low alpha track.
Yeah, so very nice talk, thank you. So in the example star formation rate history that you showed, it seemed like more of a gradual decline, and I guess I'm wondering, is that enough to produce like an actual bimodal? Like I would have assumed, I would have expected from that star formation history that it would have been more of a, like less of a valley in between the two.
Some of them drop more suddenly than others. This one has the lowest, like, absolute star formation rate. Like, you can see that's not even that, like, high to begin with. So I think that might just be because this is the lowest mass of the 4 galaxies, so even that was enough to cause this feature. But, it's always after some either, like, bump or it was higher up and then went down.
Okay, let's thank the speaker once again.